Now that we've seen and slowly dissected this huge definition of what it means for something to be a group, I think some examples and non-examples would be very enlightening. So I wanted to do just a few of these in a video, and then in class together we'll practice a whole lot more examples and non-examples. So first, let's start with a non-example. The natural numbers under addition are not a group. Now the natural numbers are closed under addition. If we take any two natural numbers and add them together, we will get another natural number. And a fact that we're very comfortable with from grade school even is that addition is associative, and that holds on all number systems that we're familiar with, natural numbers, integers, rationals, etc. However, we run into a bit of trouble when seeking out an additive identity. We are comfortable with the fact that any number added to 0 gives us that same number back, and so 0 really is the answer for what we want for an identity element in our set. However, as we've discussed previously, computer scientists think of 0 as a natural number, while mathematicians generally don't. Even if we were to think like a computer scientist and group 0 in with the natural numbers, we would still fail when seeking out inverses, because for any natural number, its additive inverse is its negative, and that is an integer, not a natural number, and so we would fail the inverse property even if we were willing to take 0 as a natural number and we satisfied the first three properties. So just as we saw with the binary operation, failing even a little bit at any one of these four criteria is enough to make a structure not a group. However, the problem that we encounter in number 4 hints at a way to find a solution to the natural numbers failing to be a group under addition. Just as we needed to expand the natural numbers in order to include 0 for item number 3, if we're willing to expand the natural numbers and take into account all negative numbers as well, this would resolve the problem that we're experiencing in bullet points 3 and 4. And changing the natural numbers to the set of integers fixes both of the issues we've encountered. So while the natural numbers fail to be a group under addition, the integers are a group under addition, and they're a very good, classic, familiar example that help take that big, scary definition and make it feel a little bit more comfortable. I'd like to do one more example, which is a very strange and unfamiliar example to show you just how broad the definition of a group is. So what I'd like to do is show you that the set of all bijections on the numbers 1, 2, 3 is a group with operation function composition. Now a bijection is a function that's both one-to-one and onto. And if you'd like to put on your fancy pants, you can say injective for one-to-one and surjective for onto. I tend to use the words one-to-one and onto since they're a little more descriptive and a little more comfortable when we're starting out learning. A function that is one-to-one is one with the property that every single output you have comes from precisely one input. So the picture I've shown over on the left is not a one-to-one function because when I look at the number 1, there are two different inputs that yield that same output. We want everything to look like it does for the number 2 in order to have a one-to-one function where there's just one thing coming from it. The function over here on the right is an example of a function that is not onto. An onto function means that everything that's in the range is also in the image. 3 is an example of a function that is in the range, but it is not in the image of the function. There's nothing that's pointing to it from the domain, and so this would be an example of a function that is not onto. Another way that you could think about it when we have a finite set here of the numbers 1, 2, 3, everything over here should have an arrow going out, everything over here should have an arrow coming in, exactly one arrow. You can think of bijections like a shuffling or a rearrangement of these numbers when you're dealing with bijections from a finite set to itself. So that's just a review of what a bijective function is. Let's now go through those 4 group properties for this particular set and operation. It is a fact that you can see demonstrated in this diagram that composing 2 bijective functions yields a bijective function. And the way that we compose them is to apply what I sometimes call the forgetful functor. So the function composition is, let's just do one function and then do the other function. Overall in this function composition, 1 maps to 2 and then 2 maps to 1. So altogether, 1 maps to 1, forgetting about what happened in between. Now 2 maps to 1 and 1 maps to 3, so altogether in the composition, 2 maps to 3, and 3 maps to 3 and 3 maps to 2, so altogether 3 outputs to 2, and that's the composition of these functions. But the composition of 2 bijective functions yields another bijective function, and that shows that we have a binary operation in function composition in this example. As it turns out, function composition is associative. We're going to have one more slide on that associative property, but verifying that function composition is associative for this example would be a lot to handle. So let's just say it is associative, and we'll come back to this point. Our identity function is going to be the function y is equal to x, but it looks a little bit different when we're representing functions in this blob to blob type diagram with arrows in between than it does when you're graphing in the Cartesian plane. All this means is when x is my input, x should also be my output, and I should have straight lines going straight across in my little blob diagram. And inverses are meant to be an undoing. So wherever I send an element in the first map, I'll just send it right back in its inverse map. So you can see here, now that we know what the identity function looks like and we know how to compose functions, 1 maps to 3, 3 maps to 1, so all together 1 maps to 1. 2 maps to 1 and 1 maps to 2, so all together 2 maps to 2. And a similar situation with 3. So we've got inverses, we've got an identity, we've got closure, and we've got associativity. Therefore, we have a group. Now I'd like to return to that note on associativity to tell you a little bit of a story. And the story is, associativity is a weird property. Of the 4 group properties, it's always the hardest one to prove, and it involves a lot of symbol pushing. So most often when we are doing examples in class, we will not prove associativity. We'll just assert that it holds for a handful of familiar operations. It's easy once we start dealing with groups that associativity is actually a very useful property. But it's very difficult to justify why on earth associativity is necessary in order for us to have a group. So associativity can be a very confusing point when you're just learning about the definition of groups because you need it and yet you don't really see why. My short answer for why we need associativity is that we are currently learning group theory out of order from how group theory was created, which is a very common thing in mathematics. What we're learning when we're learning that definition of a group, it comes from Arthur Cayley, who first created that definition in 1854. However, group theory has been going on since 1770, and in that 80-year time span, a lot was happening, and Arthur Cayley was studying one thing that seemed very different from what everyone else was studying and calling abstract algebra and group theory, and he was really the first mathematician to realize that what he was doing was secretly the same as what these other mathematicians were doing. And the other mathematicians were dealing with lots of commonplace operations that we very well knew to be associative. The reason that this associativity doesn't necessarily make sense as to why it ought to be there is it's really necessary to tie what Arthur Cayley was doing in with what historically all the other mathematicians were doing in group theory at the time. So it was just a thing that was needed to patch and bridge these two very disparate fields at that moment in time in history. So it's a great story. If you go on ever and take Abstract Algebra 2, you can get to see and experience really how group theory was born and gain a better understanding about how group theory came about.